Oh, thank you. Forgot it. See? I forgot.
Excellent.
Thank you, Julia.
Well, that was the cue, I think, to start.
He got voice. Okay, next time we.
So today I will, in this coming hour, discuss the notions of K-theory and Morita equivalence of C-star algebras. Let's first recap a little bit what we saw yesterday. So G is a locally compact group, and what we did yesterday was we constructed two C-star algebras, C-star G, the full C-star algebra of G, and C-star reduced G, the reduced C-star algebra of G. And we introduced this notion of the primitive ideal spectrum, which for C-star of G turns out to be the unitary dual, and for C-star reduced of G, it turns out to be the tempered dual. And as topological spaces, so to each C-star algebra, you can associate this primitive ideal spectrum, this topological space, but as topological spaces, they are somewhat pathological. So they are T0 spaces, these primitive ideal spectra, T0 spaces, but not much more in general. So trying to study these spaces using algebraic topology is not gonna yield very much a priori. And that's why we take this viewpoint of non-commutative geometry, which is that a C-star algebra is a space of, or an algebra of functions, I should say, an algebra of functions on some non-existent space. And so we're going to study, instead of studying this primitive ideal spectrum directly, we're going to study the C-star algebra C-star G, and in particular C-star reduced of G. And we will say that its non-commutative algebraic topology will hopefully tell us something about this tempered dual. I ended yesterday with the following. So that there is a star homomorphism, C star of G to C star reduced of G, extending the identity map So I take the identity on the compactly supported functions, and then I take these two completions, I get some map. Actually, I don't know if this map has a common name, but it doesn't really matter. So the map C star G to C star reduced G is surjective, but not injective in general. And it is injective for those of you who know what this means, when G is an amenable group. And so in that case, G hat is G hat temp. But this is a very special case. So in general, this map is not an isomorphism. and that encodes for the difference between the tempered and the full reduced dual. And this also shows you that this is really built into the analysis, because on the algebraic level, if you would say that CC of G is algebraic, I mean, it's also analytic, but for a discrete group, you would look at a map, the identity map on the group ring. This kernel you can really only see once you introduce analysis into the picture. So that's always a good thing to keep in the back of your mind. So now we're going to study, or now I'm going to, for the main part of this lecture, leave the group C-star algebra picture and again work with some general C-star algebras to explain what we mean by non-commutative algebraic topology. And I will talk about K-theory of C-star algebras, which is a large area of mathematics. There's many books written about this, so if you really want to learn it, you can pick up a book and start reading. And in this lecture, since I have only one lecture, I will sketch the main properties and motivations for this theory and indicate how it works. So we want to work with a certain category of C-star algebras. Objects are C-star algebras, and the morphisms are star homomorphisms. So there's nothing special going on here. This is really the natural categorical structure that you can think of on C-star algebras. And K-theory is a functor from, so I'm going to write K star here, from this category C star to the category of abelian groups. And it takes a C-star algebra A and it associates to it this graded abelian group K star A, which has two components, K0 of A and K1 of A. So there are in fact two groups, but it is often convenient to just think of them as one graded abelian group. And two groups have some different descriptions, but we will also see that in fact you need only one of them to understand everything. We will get to this. So this is a functor, so in the sense that if I have a star homomorphism of C-star algebras, then I get from that a map of abelian groups on the K-theory. That's the kind of functoriality we're talking about. So now let's describe K-theory, and this will go into some steps. Our group C-star algebras, when the groups are not discrete, they don't have an identity element, they don't have a unit. So they are rings, but there's no unit in these rings. K-theory is most easily described when the C-star algebra in question does have a unit, so I'm going to do that first and then indicate how we deal with the non-unital case. So I'm assuming for now that A has a unit. And then the first description of K-theory goes through projective modules. So this is a purely ring theoretic description. So a module P, maybe wait, let's say the right module, because we're dealing with non-commutative rings, right and left is always important. And that's not true that every right module is also a left module. So you need to fix a convention from the start. So a right A module P is projective if there exists an in N and a right a module Q such that the direct sum of P and Q is isomorphic to a free module of some rank. Okay, this is a familiar definition from projectivity from abstract algebra. And then a quick definition of K0 of A, the group K0 of A, is to take finitely generated and projective modules, take isomorphism classes, I will write it in a minute, and then take formal differences of those. So P is the isomorphism class as a right projective module of P, and the difference that I write in the K group here, this is a formal difference. But there is also a relation, namely addition will be, so the direct sum, this is a relation that we impose on say, a certain free abelian group. And the sum in the K group corresponds to the direct sum of projective modules. But the differences are formal. You cannot subtract two modules on the nose from each other. So we complete the projective modules into this group K0 of A. Okay. Let's say that if X is a compact Hausdorff space, then K0 of the continuous functions on X is isomorphic to K0 of X, where K0 of X is the Grothendieck group of locally trivial finite dimensional complex vector bundles on X, and the isomorphism is implemented by, well, say the Serre-Swan theorem, where you take a vector bundle E over X and you send it to its module of sections. And from the Serre-Swan theorem, we know that the module of sections completely determines the vector bundle up to isomorphism, and that's where you get this map from. Okay, so this is the most algebraic picture of K0, and in topology you directly get a relation to the Grothendieck group of vector bundles. Second description is via projections. In matrix algebras over N, over A. So there, well, first let me say, projection in a C-star algebra is an element P in A such that P squared is P star is P. So this is in analogy with projections on Hilbert spaces. Then there is an equivalent description of K0, which says, okay, we take formal differences of certain equivalence classes of projections. So P is in MNA, Q is in MA, and P star is P squared, Q star is Q squared. And again, these are formal differences. We have the relation P plus Q is P plus Q, where P plus Q is now an element of a bigger matrix algebra. So we have to allow for all the matrix algebras of arbitrary dimensions if we want to make sense of this addition. And we say, so this is an equivalence class, and P is equivalent to P prime if and only if P is U star P prime U for some unitary U in some MK of A, where we also identify P with any version of P that may occur in a bigger matrix algebra in this way, where we add zeros. If I have a K by K matrix and I just supplement it with zeros to make it an M by M matrix in this way, then that will still be a projection. And in the construction of this K group, we make those equivalent. So the same projection can occur in matrix algebra of different sizes. So this is a more hands-on description of specific elements, and to see how it links to the first description, using that for finitely generated projective modules P and Q, well, not and Q, for finitely generated projective module P, there is Q such that P plus Q is A to the n. Then it follows that there exists a P is P star P squared in Mn of A. That's now the same n as the n in A to the n, such that P as a projective module is isomorphic to the compression of A to the n by P. And so this means that from such projections, you get a projective module and vice versa. So if you have a projection, you take this projective module. If you have a projective module, you take some module that trivializes it into a free module, and then you get the projection by using that isomorphism and just projecting onto one of the components of this direct sum here. There is a caveat. So for those of you who are more familiar with algebraic K-theory, in principle, you would only get idempotence. So the star condition would not necessarily be satisfied, but because C-star algebras have extra analytic structure, you can fix that by using some functional calculus tricks. But yeah, it's always useful to realize that K0 in fact is a ring theoretic invariant. So the analytic structure of a C-star algebra comes in handy to prove certain things and compute K-theory groups, but in principle, the invariant is algebraic. Okay. Now, I will say quickly something about K1 of A. So K1 of A, I'm going to define it sort of dirtily. I'm going to say it's pi 0 of GL of A, where pi 0 means the set of connected components, and GL of A is the direct limit of the groups GLN of A. Well, maybe I shouldn't. Well, yeah, I can work with GL. But no, maybe I don't want to do that, sorry. So this was correct, but not convenient for us. I'm going to use the unitary group. Just because we can. So the embedding of UN into UN plus 1 now goes like this. So we identify unitaries of different sizes, and we take the direct limit of these groups, and then we get some topological group of which we take the connected components. But you can also say K1 of A consists of homotopy classes of unitaries of arbitrary but finite size. So the description of K1 of A looks somewhat different. I don't want to dwell on it too much here, because we will later see that K0 and K1 are actually closely linked. But philosophy is, if you have a projection somewhere in some matrix algebra, you get a K-theory element. If you have a unitary somewhere in some matrix algebra, you get a K1 element. And these are the groups. So let me say something about the functoriality. So that's where the projection and unitary picture becomes easy. So if phi from A to B, should start is a star homomorphism that preserves the unit, so we'll say it's unital, then phi star K0 of A to K0 of B is defined to be phi star of P is just the equivalence class of phi of P, where it's applied to each matrix entry, and the same for K1. Just push forward. And then you get a unitary again, or a projection. Okay, now if your algebra doesn't have a unit, you need to modify these constructions a little bit. That's because, well, not having a unit corresponds to having some sort of non-compact space, and this forces you to think about vector bundles, and you want to somehow control the behavior of the vector bundles at infinity. And that's why you have to modify the definition. You could take, well, at least for K0, you could use the same definition, but it turns out to not yield quite the right thing, because we want to build a nice functorial theory with exact sequences and other kinds of properties that I will say something about. And this means that using the naive definition simply doesn't work, as it often is the case in mathematics. So if we have a non-unital algebra, and by which I mean a unital algebra is also a non-unital algebra. So in fact, what I'm going to say will apply now to any C-star algebra. So if A is a C-star algebra, then we define A plus, called the unitization, as a vector space is just A plus C or as a set. It's A plus C, and we define the following multiplication on it. Mu A plus lambda B plus lambda mu. So this defines a multiplication on this vector space A plus C, and you see that the components interact. So this is not just a direct sum of two algebras. And A identified with A comma 0 in A plus is an ideal, and the map from A plus to C is a star homomorphism, it's just surjective. And this gives us an exact sequence. So from A into A plus onto C, and there is actually also a homomorphism S from C to A plus, which just takes lambda to 0 lambda. And this is the splitting of this exact sequence. And then it turns out that, you prove some properties of the K-theory for a unital algebra, and then you see that the following definition, namely that the K-theory of A should be the kernel of, let me call this homomorphism phi, of the map from the K-theory of the unitization to the K-theory of C, which are now both unital algebras, so you can apply the definitions I gave and use this induced homomorphism, and then define K0 of A as this kernel. Same for K1 of A. And it turns out that when you do this, you get the right functorial theory, but we have the fact that K0 of C is isomorphic to Z, and K1 of C is always 0. So you see here that the definition of K1 could also be given by just saying that the K1 of A is just the K1 of its unitization. And then you can just look at unitaries in the unitization that satisfy the required axioms. All right, that's K0 and K1 for non-unital algebras. There is a third picture that I want to briefly mention, because in practice, what did I do? In practice, this is quite powerful, but we cannot elaborate on this too much. But especially when working with non-unital algebras, this third picture is often useful. And so the Kasparov picture, I will call it, of K0 of A is the following. You take equivalence classes of triples, not be able to So here x0 and x1 are Hilbert C-star modules. So write Hilbert C-star modules over A, and F is an adjointable operator from x0 to x1, such that, as I wrote in the set already, we take two Hilbert C-star modules and some adjointable operator between them, such that F star F and FF star are almost equal to the identity, where we say that they're almost equal if the difference F with the identity is compact. And this, if you have P and Q projective modules, you can get an element in the Kasparov group by taking x0 is P, x1 is Q, and F is 0. This is the Kasparov element that you then get, and this gives the map from one picture to the other, which turns out to be an isomorphism. The reason that the Kasparov picture is useful is mainly technical in proofs, and that's why I want to mention it. I will use it once when we discuss Morita equivalence, but it makes it unifies the pictures of K-theory, and it puts emphasis on operators on Hilbert modules. Okay, so and the equivalence relation on such triples is some form of homotopy. Again. All right, so these are ways we can think of K-groups. Now let's discuss some properties. So we already discussed the functoriality. I'll put it here again in words. So functoriality for star homomorphisms, meaning that if you have a star homomorphism between C-star algebras, you get a map between the K-theories. Now, the following important property is that if I have a short exact sequence of C-star algebras where I is an ideal in A, and this map is an inclusion, and this is a kind of quotient map, of course, so these are both star homomorphisms, I injective and Q surjective, then we get a long exact sequence in K-theory so here we come from K star plus 1 of B. So these are boundary maps, and these are just functorially induced maps. And so this already starts looking a bit like a cohomology theory. In fact, it's even better. So this sequence a priori is a long sequence, like it will go on forever, even though I have not defined the groups beyond K1, but the previous result should be combined with what is called Bott periodicity. And this is an important, very important result in the K-theory of C-star algebras. One of my teachers, I don't remember who, would say that this is actually the only theorem in K-theory. So let me briefly explain what Bott periodicity is about. If I have a C-star algebra, I can form its suspension. We can look at the algebra that comes from functions, continuous functions from the open interval 0, 1 into my algebra, such that f0 and f1 both vanish. This is called the suspension of A, and it's, for those of you familiar with algebraic topology, it is related to the suspension in algebraic topology. But if you track down the definitions for a commutative algebra, it's not exactly the same, but it turns out that homologically the definition is the same. And then this is sort of part of the exact sequence that I wrote in the previous point. If you set as a definition,
sorry, Bram, the domain does it include 0 and 1 or not?
No, it doesn't. It's the open interval.
And f of 0, f of 1 means?
Well, it means that if you take the limit going to these points,
Okay.
you get 0. Yeah, okay, I could have taken the closed interval if you want to be very, maybe that's more precise in this formulation. Thanks. So the higher K groups you would define as the K0 groups of the nth suspension, where it is easy to show that K1 of A, as I defined it, is actually always isomorphic to K0 of the suspension. And that motivates the definition of the higher K groups in this way. And the Bott periodicity theorem, which is not easy to show, says that K0 of two suspensions is actually the same as K0 of A. So this is a remarkable result. There are many different proofs of this. A proof I particularly like is due to Joachim Kunz using Toeplitz extensions. It's quite powerful. You can formulate these proofs by just using abstract functorial properties of K-theory, actually. So you need homotopy invariance, Morita equivalence, and split exactness, for instance, and then you can play even with these properties to get optimal results. But so this is somehow a structural result, that the K-theory of this double suspension brings you back to degree 0. And as a corollary, this long exact sequence that I have there is actually much shorter. It becomes the famous exact hexagon, or 6-term exact sequence, where the vertical maps are the boundary maps and the horizontal ones are just the functorially induced maps. And this is one of the main computational tools in K-theory. These boundary maps can be sometimes hard to compute, but they exist and they are functorial and everything. So in the end, we see that we have a homology theory, we have groups in each degree. It turns out to collapse due to Bott periodicity. And this means that we get from short exact sequence of C-star algebras, 6-term exact sequence in K-theory. One last property we will need is behavior of K-theory with respect to so-called C0 direct sums. And here, suppose we have a countable family well, it doesn't even have to be countable. Let's say a family of C-star algebras, then we can take the direct sum which would be functions from the index set to the disjoint union such that Fi is in AI. And a priori, so a priori, Fi is 0 for all but finitely many I. And now we need to complete this. So we need to take a completion such that for every epsilon greater than 0, Fi is less than epsilon for all but finitely many I. And this is the C0 completion, so this means that you look at sequences not that are eventually 0, but that become small once you go out to infinity, where you take the compact sets to be the finite sets. So this is an analytic completion of the algebraic direct sum, and this is what we will see when we look at the K-theory of C star G. If you take this C star algebraic direct sum, then the K-theory distributes over that, where this is now the algebraic direct sum of abelian groups. So if you have a decomposition of a C star algebra into such a direct sum, then you can compute the K-theory by computing the K-theory of each component. Okay, I see that time is running, so let's talk about Morita equivalence. C star algebras, and this is after isomorphism the most natural equivalence relation on C star algebras, and you could even argue that it's more natural than isomorphism. Well, more natural. It's less rigid, so it allows you to introduce some freedoms in the computations that you do. So I will define it straight away for you. Let A and B be C star algebras. We say that A and B are Morita equivalent, and we write that like this. If there exists a Hilbert C-star module X over B such that A is isomorphic to the compact operators on that X. Now there are many things to say about this definition. First of all, it's not clear that this even defines a symmetric equivalence relation. I will say something about that in a moment. But let's first see what this means. So A is always Morita equivalent to a finite matrix algebra over itself. And the module is A to the nth. So that's the simplest algebraic instance of Morita equivalence. But we also have that C is always equivalent to K of H, where H is the separable Hilbert space. And the module is then H itself, with C acting on the right and K of H acting on the left in the usual way. So here in the second example, you see that a unital finite dimensional C-star algebra can be Morita equivalent to a non-unital and infinite dimensional one. And okay, I haven't treated tensor products, but you can maybe guess what this means. So if I take an arbitrary C-star algebra and I tensor it by the compact operators on some Hilbert space, then that's also Morita equivalent to A itself, and the module would then be H at tensor A. This, I guess I won't have time for that, but these are completed tensor products. So this is not just the algebraic tensor product that you know from ring theory. You need to enlarge them a little bit to get a C-star algebra again. But so you see that this relation is already pretty flexible, and these are sort of abstract examples. Let's comment on the symmetry.
Bram, can I ask a question?
Yes.
Do you need fullness for the Hilbert module here?
Oh yeah, you're right, I think. Wait. I have not defined that. So there exists that is correct, a full Hilbert C-star module, and full means that this set of inner products is dense in B. That's right. So you cannot just take any C-star module. This is an important point indeed. You need that the inner products, the values of the inner products, see the whole algebra. Right. So we see these sort of more algebraically motivated examples. In due course, we will see some examples of Morita equivalence coming from loop actions. First, the symmetry of the equivalence relation. Well, if XB is an AB bimodule with A isomorphic to K of this bimodule, then there exists a dual module, which is now a left B module and a right. So I'm going to write K of X here also, because K of X always acts on the left. And this module is actually can be concretely defined well, I could have this is a funny way. This set I'm defining here is just k of xb to b. So there is a dual module, and I will not go through the definition, but we saw that the space of compact operators between two Hilbert modules is always defined. And it turns out that this dual module has some nice properties with respect to the tensor product of Hilbert modules, which I also haven't defined. So if you have a Morita equivalence between A and B, then it turns out there is a dual module which is a Morita equivalence between B and A. So X star is an equivalence between B and A. And that gives you the symmetry of the relation. Now, let's discuss some more geometric examples. So this is actually a theorem example, and the next one too. Both are due to Riefel. So let X be a locally compact Hausdorff space, and G acting on X a free and proper action. Of a locally compact group G. Then the C0 functions on the quotient space X mod G, which is a nice locally compact Hausdorff space because the action is free and proper on X. So that's a nice space of functions, is Morita equivalent to the cross product of C0 of X by G. And this cross product we constructed in the previous lecture. And important thing to notice is that this object here exists for any action. So if I have a group acting on a space, then C0 of X becomes one of these GC-star algebras. This object always exists. So whereas the other side of this equivalence doesn't always exist, this only exists for free and proper actions. And so you see that for non-free and proper actions, the cross product is a replacement for the quotient space. It's an object that we can have play this role, and it generalizes the quotient space in this sense. And the bimodule, so the bimodule is in this example, is a completion of CCX. With inner product given by integrals over G. So here X is in the quotient space, and X in X is a choice of elements such that well, I cannot say that like that. So X is just a lift, a chosen lift of this element in the quotient. And because we integrate over the group here, it doesn't matter which one I choose. So you see that these Morita equivalences also arise from geometric setups. And so this is much more geometric, analytic, intrinsic, where you can write down these structures, which is often more useful than the more algebraic examples that I gave in the first place. And another important result, also due to Riefel, example theorem. Due to Riefel. So let H and K be closed subgroups of a locally compact group. Then we view one of them as acting from the left and the other as acting from the right. So these are commuting actions. And we have that, and I'm going to write it like this. I mean, I have introduced only the cross product notation from the right, but you can imagine using a left action, there's nothing fundamentally changed. I should not write isomorphism, but Morita equivalence. So if I have two subgroups, then the two cross products that I can associate to these subgroups are actually Morita equivalent. And here you see again the interplay between quotients and cross products. So I take a quotient by one group and I cross by the other, or the other way around. I get a Morita equivalence. And the bimodule here is a completion of CCG. I will not elaborate on the details. I think I should stop here. Didn't get as far as I wanted, but I can integrate the remaining material in the next lecture.
All right, thank you, Bram. Let's keep the recording running. If you have questions, it's good to include them. Thank you, Bram. Thank you very much. Any questions or comments to Bram, please? Okay, that seems to be now. So we could also, there will be a third lecture, so you could also catch Bram for the third lecture. All right, then let's stop the recording, Juliet, if you're hearing me. Let's see.
Okay.